So as we get set up, I want to just welcome you all to the NREL, North Central Climate Science Center, and the Ecosystem Science and Sustainability Departmental Fall Seminar. The seminar theme this fall has been Managing for Climate Change. And today we have the honor of having Berrien Moore talk about some of the current plans for geoCARB, which actually is really kind of really an important sort of aspect of the Paris Agreement of looking at how do we actually monitor for carbon changes. And so having today the sort of the initiation of the Paris Agreement going into effect is sort of opportune to have this sort of presentation. Berrien has been recognized as a leader in global change research for many decades, especially working domestically with NASA and NOAA. Beyond leadership teams there, and being recognized as a leader in this area. He initially started this work looking at carbon modeling. I guess when I first met Berrien in the 80s, he was still working with these sort of 8-box models, 12-box models of the ocean. He's really come a long way since then, working with Earth system models and being really a leader in that area. Also had the fortunate opportunity to work with Berrien when he was the executive director of IGBP, and really was formative in trying to develop an Earth system perspective among the major programs at that time in the late 1990s, early 2000s. He continues to work. He's now sort of working in a parallel center as ours. He's the director, university director and lead for the South Central Climate Science Center, sort of a partner organization to ours. And he comes to us from his sort of dean position at University of Oklahoma in the College of, I'm not sure what college it is.
Geographic Sciences.
And with that, I'll turn it over to you.
Okay. Well, the only problem with that introduction is when he says he's known me for decades. Certain ring to the word decades that I'm a little sensitive to. There are two aspects of this: the geoCARB mission that we'll talk about towards the end of my talk, and then what I call is Faustian bargain. I don't use the word Faustian bargain in a negative sense in terms of a pact with the devil, though the devil is always in the details. And the fact that when you burn fossil fuel, you release by the act of burning, I mean, by definition, you're going to get carbon dioxide out. And in terms of organic material, if you don't oxidize it, the other way that you get it out is kind of God's back door on the carbon cycle, and that is methanogens, and so you get it out as methane, also a greenhouse gas. Now, methane is not long-lived, but when it oxidizes in the atmosphere, it becomes CO2. So you have this problem, and CO2 is perfectly okay. It's not poisonous. I mean, you can. I was on once on Ira Flato's Science Friday, and we were talking about carbon dioxide. I said CO2 is building up about 0.5% per year. And then you go to call-in. People call in. And the very first calls came out of Utah. It was a female from Utah, and she said, "I'm not a scientist, but this scares me because we'll all be poisoned." And I said, no. That's carbon monoxide. Carbon dioxide is just what we breathe out, what plants take up. It's not poison, it's just a high concentration leads to climate change. And she said, oh. And I said, yeah, in fact, it's not poison, she said. And I said, no, in fact, on Friday, like today in the halls of Congress, CO2 is probably 6 times normal just because of everyone. And she said, without listening to me, oh, it's not poison, it just makes you crazy. I've never forgotten that. So, let's see, where do I point? Oh, there we go.
I have to initiate it first here.
Can I just do it here?
There we go.
Okay. Yeah, this is what I'm going to start with.
And I think
Do you want me to do it, or is this going to work? All right, I want to separate out because there's a lot of confusion on the climate topic. And many times we confuse what we know for sure with what we don't know. And it all gets blended together. So I'd like to break it out in 3 separate parts: what we know for sure, what we think we know, and what we do not know. And then in the area of what we think we know, I'm going to come back to that towards the end. What we know for sure, and this is what we know absolutely for sure, the Keeling Record. I think everyone here knows the Keeling Record. Concentration of carbon dioxide over time, starting in 1958. This was part of the US contribution to the International Geophysical Year, IGY. One of the great things about IGY was the Soviet Union put up Sputnik, and a postdoc from Scripps, David Keeling, started measuring CO2 at Mauna Loa. I'm not sure which had the more lasting, but certainly both very important. And I talked to Keeling about 10 years ago, in fact, down at NCARB, and I asked him, I said, David, what did you think when you first started making this measurement right here, and you see CO2 was going straight up? What did you think? And he said, I thought I had a little problem. I wasn't sure what it was. And then I said, what did you think, David, when it turned around and came the other way? And he said, I thought my postdoc was over because clearly I had an instrument problem. And then when it turned around and went the other way, and you realize that you're measuring the annual cycle, the drawdown in spring and summer, the northern hemisphere, upward increases, respiration dominates in the fall. I said, what do you think then? And he said, Nobel Prize. Now, he didn't get it, but he should have, because this really was it. And this is where he started making the measurement, as you know, on the Big Island. And you see Mauna Loa was established just before he began making the measurement. Here you see something you don't normally see in Hawaii, snow, because you're at about 11,800 feet. And there is the building. This is the Keeling building. This is the air intake. And I'm going to focus in on this right here. I'm sure many of you have seen this, but it's important. It's my life and the Keeling Record. So really, it's the Keeling Record. It's the Keeling building. And I think if you looked at observations of the 20th century, I think you put the CO2 observation right up there with the observation of the speed of light in terms of profound, lasting scientific importance. Nowhere near the theoretical thing, but in terms of importance to the planet, this is a big deal. This was a celebration of the 40th anniversary. And I think that if you think about it for a while, and if you looked at this and you've looked at it in your studies, you don't even need to have the axes. In fact, I think this image ought to be on every single gas pump on the planet. I think it ought to be on your utility bill. And in fact, my goal is it ought to be as familiar to the body politic and to the citizenry of the planet as the Mona Lisa. So another thing I'm sure many of you have seen, and this is the ice core record. This is the Antarctic record from the Vostok core. This goes back 4 ice ages. It actually now goes back 7. But it stretches it and makes it hard to see, so I just chopped it here. But what I find really remarkable, but the more you think about it, it's kind of not remarkable, it kind of makes sense, is that this repetitive pattern of the decline of CO2 concentration from around 280 parts per million down to about 180 parts per million. That's what the axis over there is. And then the fact that this repeats itself each time. I think that's rather remarkable, but I'll come back to why it's kind of natural. The other thing that's interesting is it goes into the ocean slowly. If you think about what's happening as you come into an ice age, first of all, you're losing many of the terrestrial forests of the northern hemisphere. And so not only are you getting rid of carbon that is stored on the land, which probably goes into the atmosphere almost certainly before it goes in the ocean. So you're dumping carbon into the ocean at the same time it's having to go into the ocean. So a tremendous amount of carbon is moving from the land to the ocean via the atmosphere as you go into glaciation. And then that carbon comes out rather quickly. Now that's kind of interesting. That means somehow it didn't get that deep in the ocean, but gee, 150 million years? How does the ocean, I don't really understand that. That's something I really have never figured out. Now, the reason I think that it keeps coming back to these set points of 280 and 180 is really just kind of the temperature. In other words, there's a certain kind of average temperature of the planet, and that more or less partitions how much CO2 there's going to be in the atmosphere, how much there's going to be on land in various ecosystems, and how much is going to be in the ocean. because the ocean CO2 transfer is largely dependent upon temperature. If you warm the ocean, you're going to outgas. If you cool the ocean, you're going to ingas. And that's exactly what's happening here. As you cool the ocean, as glaciation comes out, you allow more CO2 to be taken up because of solubility. It's more soluble. So somehow this takes the available carbon in the active pool, how much available carbon we have, how much we have, and it partitions it between the atmosphere, the oceans, and the land based kind of around temperature. I think that's what's happened. So now, this is really interesting. Suppose, let me just go back. Suppose you change the amount of carbon in the available pool. Then you start saying, well, there's going to be a new set point in terms of where the atmosphere is, because we're making more, think of it as a monetary problem, like you're inflating, you're printing money. People talk about inflating the monetary cycle. We're just inflating the carbon cycle, nothing more. Here's actually the inflation, and it's very nice. This is the Greenland core that actually Paul Majewski at University of Oklahoma, New Hampshire, I was kind of Freudian, New Hampshire, who's now in Maine, and others, they were very active in taking this core. And you see two things, I think, really quite remarkable. This is a little ice age when things are very cold in the Northern Hemisphere. You actually see a decline in CO2 below the 280 mark. This is the parts per million over here. So you actually see kind of a climatological aspect here, the little ice age kind of at around 275. And then, of course, the Industrial Revolution, the late 18th century Industrial Revolution. And the green is the Keeling, is the annual average of the Keeling data. So the ice core data hits exactly the Keeling data in terms of the concentration. Ice, of course, has got this historic record because when snow fell, got a little bit of the atmosphere. I'm sure you've seen that. Okay, why is it? This is the cumulative CO2 release. It's an old figure from 2007. I got it out of Oak Ridge National Lab. They haven't updated. I have to figure out why I haven't updated. This is an important thing. This is the cumulative release of CO2. This is essentially the inflation, if you will, of the carbon cycle. And it's the cumulative release that's important because that's how much kind of stays in the atmosphere, in the land, or in the oceans. Cumulative. This is the carbon printing press. This is the inflation factor. Okay, now let's just look at a couple of policy aspects of this, because I want to connect it to something else we know for sure. This is the CO2 emissions. I've changed the unit slightly now. I'm looking, because it's economists like to work with gigatons of carbon dioxide. Geoscientists like to work with gigatons of carbon as CO2. So this is in the gigatons of carbon dioxide, and this is the growth rate. And what do you see here that is really unusual, I think, is that. And that's the global recession, 2008-9. So in the global recession is expressed in the emissions data. This is by country. And what's interesting is China never saw the global recession. Now they're seeing a little of it now, but we sure did, and Europe sure did. India did not. And so this looks at this. Now, let me say something. You know that this is something that's very political. People say, China is the problem. This is data that is, shall we say, we look at the emissions from China. What if we change the data and looked at the embodied emissions that would also include imports or exports? So if we have offshored a great deal of carbon producing manufactured goods, and then we imported them into the country, then should they be in here or should they be in here? So that's something to look at. Also, you have to look at the cumulative release. And if you look at the cumulative release, because China was for so many years under the world's average of cumulative, the US still by far leads in the cumulative release. And in fact, if you look at per capita, then the US also leads. China, it's interesting, China and Europe, the European Union, just have about the same per capita release, which is very interesting. Now, this is something I think is really bothersome. And that is, let's look at the curve of, over time, of energy intensity. And that's in some sense a measure of efficiency. What is what is the CO2 production per GDP? So if GDP goes up faster than CO2 is going up as an emission, then you're getting more efficient. GDP is increasing faster than CO2 emissions. You're getting more, it's an efficiency measurement. So emissions intensity is an efficiency measure. So now let's look at, over time, GDP against energy emissions efficiency. Let's say, just take a piece of it. GDP goes from 40 to 80, doubles. But the intensity efficiency doesn't double. So even though we're getting more efficient, our GDP growth rate is outpacing our efficiency growth rate. And that's why we're adding more CO2 every year to the atmosphere. That's why CO2 emissions are going up. We are getting a lot more efficient, just not at the same rate. So what do we know? I think for sure. CO2 is greenhouse gas, we know. Its atmospheric concentration is increasing. Its increase has been caused by us primarily. I think we know this. Fossil fuels at the center of most economic, almost all economies. I think we know that. In fact, you can see even the recession. And we know CO2 is a long-lived gas. And therefore, I think we know stabilizing atmospheric concentration in the atmosphere, stabilizing the concentration is going to be tough. I think we know these all for sure. What do you think we know? Well, you could go to the scientific literature. Michael Crichton. You know, people cite State of Fear as a nonfiction book. I mean, Michael Crichton was a fiction writer. He was a doctor. He wrote fiction. And he just made it look like a nonfiction book. Or you could go here. In fact, if you go here and see the movie again, you'll see the ocean conveyor belt. In fact, the ocean conveyor belt is right at the heart of the movie. But that's not science. So I think this is where you have to go. If you want to say, what do we think we know? This is where you're going to find it. I mean, by definition, these are assessments of the scientific literature. They are not new science. They are assessments of the published, peer-reviewed scientific literature. That's what they are. So what does that say? This is our best shot at what we think we know. So if you go back, and this one I'm going to take the third assessment, fourth assessment, fifth assessment, and look at certain statements. I was involved in the third assessment, and we thought we were right on the cutting edge of science, which is true, we were, but it was a long time ago. And so we said, this kind of provocative, an increasing body of observation gives a collective picture of a warming world. Shall we say it's kind of a fuzzy statement, but that's what we said. And then, fourth assessment report, warming of the climate system is unequivocal. So there was a tremendous amount of movement from the third to the fourth. Now it's unequivocal, as opposed to a collective picture of a warming world. Third assessment, new and stronger evidence that the warming is likely attributable to human activities. In the IPCC, and maybe Dennis, you teach this, you have to teach what these words mean. Likely means 2 out of 3. Fourth assessment, most of it very likely, 9 out of 10. IPCC, you have to have what I was a kid we called the Captain Marvel decoding ring. So if you could decode the IPCC. Fifth assessment, it is extremely likely, 95 out of 100, that the warming is due to us. Okay, so suppose you say, well, I remember, Climate Gate, and can't trust any of that stuff. This is a very interesting document. It's from the Science Board of the Department of Defense, Trends and Implications, Climate Change for National Security, International Security. If you read this is really an important document. I mean, this is really important. And it talks about changes in terms of drought in Africa that could lead to war. You could even trace, and I'm sure people have looked at this, how much of the Syrian situation is due to very poor farmers being in a drought situation, coming to the cities out of money and angry. You can also look at, with the opening of the Arctic, which I'm going to talk about, it's now the Arctic Ocean. Do you need an aircraft carrier in the Arctic Ocean? So, for 300 years and probably longer, we searched for the Northwest Passage. That, namely, how do I get from the Atlantic Ocean to the Pacific Ocean without going through the Suez Canal? That's what, I mean, a lot of explorers searched for this. And in 2007, you could have done it 2 different ways. You could have done it right around Russia, or you could have done it right around Canada. Okay. Now that is not open ocean. That's just where you don't see data because of the nature of the orbit. And this is from the radar data from NBSat, which is a European satellite. You put the data, I'm sure you've seen this. This is, but it's kind of interesting. This is the ice cover in 1980. There it is in 2007. Much thinner than that now. But most of my students, even my students that are in geography, I think we all suffer from certain geographical ignorance. How big is that? And that's how big it is. The ice cover in 1980 is about this large. So you could now look at the melt region and say, well, that's about what melted. That was the kind of loss we saw. If you go right down here to Boulder and look at the Snow and Ice Center, you'll find these charts. This right here is 2 standard deviations of this average. 2 standard deviations of this average. And this average includes 2007, 8, 9, and 10. That is when we were seeing tremendous losses of ice. So this average includes a significant change in the ice cover. So that is what you're looking at in terms of Arctic sea ice change. Now, in fact, they're shipping through the Arctic Ocean. And I guess in some kind of weird climate social feedback loop, the predominant shipping is oil from the North Sea to China being shipped through the Arctic Ocean in the summertime rather than going through the Suez Canal because it's shorter. Also, an important feedback loop is you take a bright object in the summertime and turn it dark, and that is a positive feedback loop on warming. Take the GRACE, and you'll see the same kind of thing when they look at changes in mass cover. I think this has got to be one of the most remarkable space missions because it's one of the few remote sensing missions that doesn't look at the planet. It's just 2 satellites that look at each other. And then you just look at the fact that being in orbit means you're falling around the planet. And if I fall slightly faster around the planet, the reason I'm falling around the planet is F equals ma. A ain't changing, that's the the gravitational constant. So if I fall faster or slower, that's because mass is changing as I go around the planet. I'm not talking about time. That is, that you go around the planet, there are mass distributions called the geoid. So this was put up to measure the geoid of the planet as if it were a constant. And that's, I think, what we were thinking about. Then they realized that time, year by year by year, you could look at the geoid of some place like Greenland and see that Greenland was losing mass. Well, the only way that that is because it's losing ice. Okay, so what do we think we know? It's very likely that the Arctic sea ice loss is due to us, if you will. And there's low confidence in our knowledge about the Antarctic. So I think there's something that's telling us about the Arctic. And the reason for that's kind of obvious. The Arctic is an ocean, the Antarctic is a continent, and they're different things. It's a whole different situation with the Southern Hemisphere. But there's a sense that the very likely anthropogenic influence very likely contribute to the Arctic, likely only in terms of the retreat of the glaciers, because this is a very heterogeneous problem of the glaciers. Something else I think is interesting. If you look at the 5th assessment report, a lot of things that we can say about hot and cold that are very likely. Less confident of the things we say about precipitation. And that, I think, is disturbing. I think we begin to get a handle on the hot and cold part, but we don't really understand precipitation changes. And that's actually what's the most important. Okay, the other thing we think we know is something about the carbon cycle. I'm going to say think we know. There's a lot here we don't know. I'm sure you've seen that, but it'll be a thing. It just simply shows fluxes over 2 decades. And the important thing that I want to treat right here is this land sink. And it's expressed this way. And this is a big change. Of the carbon we put in the ocean, put in the atmosphere, about half stays in the atmosphere. About a quarter goes in the land, about a quarter goes into the ocean. Now that part that goes into the ocean is just kind of the difference in partial pressure. It's complicated because the ocean is mixing, thank goodness. And when you put CO2 into seawater, CO2 disassociates, becomes partly carbonic acid, leads to the acidification that controls the partial pressure also. So this is complicated, but I think we understand it pretty well. And when I got into this game, built these little simple box models. At that time, the kind of going in assumption was that the atmosphere took up about half and the oceans took up about half. And we just couldn't come up with models that described that. But we were pretty sure we were right, even though the models kept saying, no, you're not. So we kept trying to make an efficient ocean. And as we added detail to the ocean, it became less and less efficient in terms of taking up carbon dioxide. So finally, we began to think about this afresh and said, well, maybe there's a role for the land. But I think what really triggered this was kind of a profound observation, and that is someone went back, some people started looking very carefully at the derivative of this thing, at the derivative. So slight slope changes year to year. And what they saw was the year-to-year increase was much more hectic than we anticipated. It just required looking at the derivative. I don't know why we had to do it. But you couldn't explain it by the derivative of the fossil fuel input. And we didn't think you could explain it by year-to-year changes in the ocean. That's just not the time constant you're going to see. So it's got to be the biosphere. It's got to be the biosphere that's doing this. Now, when we first started thinking about that, the oceanographers, I don't know whether they were competing for funding or what. I said, no, it's got to be the oceans, because we saw this kind of alignment. And Roger Francis, I think this was really the first thing that came out. When Francis' paper came out, it had this in it. And he started observing that, gee whiz, when you have an El Nino event, you seem to get a big increase in the atmosphere. El Nino event, big increase in the atmosphere. El Nino event, a little confusing. And then, of course, we got to the biggest El Nino that we had ever had, and we didn't get a big increase in the atmosphere in terms of the year to year. But you could say, well, we had a volcano go off. And then, sure enough, the next big, well, that is a big increase. So there seemed to be, but it's broken down. It seems to be some kind of El Nino, La Nina. And so people said, that's got to be the ocean. Well, you put an El Nino and a La Nina into an ocean model, and you don't see much change in the uptake. So it's the El Nino, La Nina perhaps being expressed through the terrestrial biosphere. But I think this was the thing that really got us all hooked. And I think this is one of the great stories. Many people, I don't know if you've seen this, but this is also a great family story. This on the oxygen concentration axis is due to Ralph Keeling, David Keeling's son, who's now in charge of Mauna Loa. And Ralph was measuring the change in oxygen over time. If you burn fossil fuel, not only are you inflating the carbon cycle, you're deflating, if you will, the oxygen. Now, it's in the 5th decimal point, so you don't need to worry about that. The lady from Utah would call us up again, but you do see a slight change, and there is a slight decrease. And so Ralph started measuring this year by year by year, using his father's data, David Keeling here, Ralph Keeling there, and plotting in oxygen carbon dioxide space where you were per year coming down. And so here these are measurements. Okay. So just take the year 2000. And then he said, if you take a reasonable estimate of how much CO2 you produce when you burn fossil fuel, this requires a kind of a fuel mixture formula, and how much oxygen you consume over that decade, you should be here if there were no ocean and no land. In other words, if CO2 were conservative in the atmosphere, didn't go anywhere, just stayed in the atmosphere, you should have decreased oxygen by this much and produced this much CO2. But you're here. Now, some people argue, well, you don't know that number that well. Okay, so suppose I tweak the slope a bit. I know that if I'm here and versus here, or here, or here, if I am below in oxygen space, that tells me that the biosphere is involved, terrestrial biosphere is involved. Why? Because the only way you replenish some of that oxygen, in other words, you need to have oxygen up here, not down here, or down this low. You got to have something that made oxygen, because you're here versus here. The only way to make oxygen is to have a net terrestrial biosphere that is bigger. The terrestrial biosphere has got to have grown. That's your only oxygen producer around. So you could argue about exactly what this slope looks like, which might then argue about how big these are slightly. But what we observe is that when you put CO2 into seawater, you don't change oxygen. It doesn't fertilize the phytoplankton. Only by going up. So this is in some sense a Redfield ratio, that slope, kind of in oxygen-carbon space. Now you could quibble about that, you know, exactly where that slope is. If I put the slope here, then it means less wet in the ocean. If I put the slope here, it means more wet in the ocean. But you still have got to go up. Terrestrial biosphere has got to be getting bigger. So that's kind of an interesting question. What is going on to make the terrestrial biosphere bigger, even after deforestation? It's got to be net. It's a net number, net bigger.
Question?
Yeah.
But is that increase getting smaller every year? Is that dot get, you know, as
That's a very good question. That's a very good question. I'll show you something later if you want to, but I looked at some Japanese data, and it goes over a period that kind of goes from 1995 out to around 2010. In other words, it goes beyond, it takes the Keeling Record. I haven't looked at Ralph's latest data, and it shows actually, if I do the partition then, that the ocean is bigger than the biosphere. Now, that could be these wobbles of uncertainty. It could be different measurement systems. I mean, CO2 is the same, but it's Japanese oxygen measurements versus Ralph's. It could be variability. I don't know, but that would be interesting. If that's true, then it would say, you know, then 6 gets smaller. That would be of some concern. This is a book. It should be in your library here. Carbon and Biosphere. This came out. I was a mathematician, and I decided I wanted to change, and so I went down to Woods Hole Oceanographic for a year, and then actually spent a year out in Hawaii and at Stanford. But in the year that I was at Woods Hole, this meeting was held, Carbon in the Biosphere. George Woodwell was the chair of the meeting. David Keeling was there. Box models galore were there, where we had 3 box models, 4 box models. And a young postdoc, Charlie Hall. And some of you may know Charlie. He's at Syracuse University, very distinguished ecologist. Charlie was there as a postdoc, and I was there after 7 or 8 years as a mathematician, but I was only hanging around the postdocs because they were all learning and I was learning, and so we were in the bar together and at Woods Hole, and Charlie's complaining about the fact that George Woodwell, the chair of the meeting, who was Charlie's professor as a postdoc, had told Charlie, I'm sorry, we're not going to take your paper, but you realize this is mainly big cheese scientists and you're just a humble postdoc. And oh, by the way, not only are we going to not take your paper, your job is to lay out the cover of this report. Charlie, over a beer or 8, Charlie said, I'm a very distinguished scientist. I'm not here to lay out the cover of a book. But, you know, the beers had taken their hold. And so Charlie started thinking about the opportunities of laying out a cover. And at that time, Charlie was dating a girl from Australia. So he said, let's just move her in a little closer. And then Charlie, and I think this was just wild. Charlie said, what if we stuck Africa here? That's not South America. That's Africa. So then we said, what we ought to do is rename the book. And then we did what we'd have is that this is only if you held the light just right, because you see this. Now you realize, this book is in your library. It's a book of the United States Atomic Energy Commission. There's Africa in here instead of South America. How would that fare in the modern American political climate? I'm not sure. But anyway, so here's what I think we know. Humans are extremely likely to be the cause. And Arctic sea ice, very likely. 90% confidence level, we're saying Arctic sea ice declines are due to us. Now we get a little vaguer. Global temperature change will change rainfall patterns. Not saying what we know. This is tougher. I think we know that there's a large terrestrial sink. We just don't know what it is. But I think we know. I think the evidence is that this is true. I think the other thing we know is you change climate, you will change the concentration of CO2. We saw that in the ice core data. Just the cooling of the ice age, CO2 in the ocean. Well, there are more positive feedbacks than that. You warm the ocean, you decrease the ability of the ocean to take up CO2. You change the Arctic and you change the albedo of the Arctic, you'll change things. Okay, what do we not know? Changes in severe weather extreme events. Extreme events are out on the tail of the distribution. That's tough. If you change anything, if you say anything about a tail of a distribution, that's tough. How sensitive is the climate system to the greenhouse gases? How sensitive is it? How strong is the climate carbon connection? How strong is this feedback? Positive and negative. How strong? We don't know about the Antarctic. And of course, what we don't know is what we don't know. Surprises will exist. So what do we really not know? I've thought about this for a long time. I don't know how they did it. How do you do it? Did you watch that game? 6-3. Then Cleveland comes back 6-6. Then the Billy Goat is kind of walking around, and Cleveland's going to win this thing. And then 8-6, and then Cleveland comes back 8-7, and then a grounder to third base, and the Billy Goat's dead. So I think that's what we really don't know is how do you swap out the energy system of the planet? How do you do this? How do you take an energy system of the planet that depends primarily on carbon and swap it out without creating havoc? I think this merits a lot of discussion. This merits a lot of discussion. I'm not going to do that now. I'm going to go to something else that I've been working on, and I'm not expert on this. But this, I think, this place, a lot of places, we ought to be talking about this. And we ought to be talking about pretty serious terms. We're teaching a course, Managing Climate Change, very much what you've been doing here. And we've actually got some business students involved. We've got some other people. And we gave them Pacala's wedges. And I don't know if you've done that around here. Talked about how you have these billion-ton wedges. And you need about 8 of them. If you're going to go from 10 down to 20, you're going to take 80%. That's about what we do. You need to stabilize. You've got to take about 80% of the CO2 emissions turn out. Well, now think about it. That terrestrial sink, whatever it is, it's up there in a couple of big, it's more than 2 billion tons C per year. It's 2 of those wedges. Whatever it is, it's there. So that's what I'd like us to think about, is something like this carbon observing system. And I'm just going to talk a small piece of this, and it's just because it's something I've been very interested in and unable to achieve. So this came out of a workshop we had at Oklahoma in 2015. And that is basically that what we have right now is kind of a sparse carbon observing framework. We have a couple of satellites, we have some ground stations, we have pieces of neon, we have some LTERs, we have some aircraft data, we have some ship data. But this is what we really need. Something that is really, at the planetary level. And it would have all these pieces. This came out this was a report that came out very early in the Obama administration, very first term. And unfortunately, it came out and they stuck a price tag on it of somewhere north of $5 billion. And with that, this report just died. And I think that's really quite unfortunate. I mean, there should have been a case developed for this, that you would have power ships and so forth. There's the Orbiting Carbon Observatory, which failed to go on orbit the first time, but is up there now. Chris O'Dell is very active on that mission, OCO2. This you could think of as GOSAT, the Japanese Greenhouse Observing Satellite. This is the kind of thing that I think we need, but we want to add a piece to that, and I want to just spend the last part of my lecture talking about it. And that is to stick a geostationary orbit, a CO2 methane monitoring instrument. Now, just to make sure we're all on the same page, geostationary orbit is an orbit that sits right on the equator. That's the way it works. And it's about 22,500 miles out. And at that radius, a stable orbit puts you at a fixed point above the Earth's surface. I once tried to explain that to Dan Quayle, Vice President Dan Quayle, when he visited New Hampshire. And I kept saying, it's stationary. And he said, well, why did it fall down? I said, well, it's moving. And he said, I think he said it's stationary. And so I went, and then finally Dave Scholes, who was a postdoc of mine, Dave Scholes said, Mr. Vice President, I hear Indiana's going to have a hell of a basketball team this year. And Quayle lit up, and I thought, oh my God, I got out of that. So just make sure you're not Dan Quayle here. It orbits at a fixed point because at 22,500 miles out, the orbital velocity keeps you at a fixed point. It's right on the equator. And that's why a lot of the communication satellites, I mean, that's where you want them. Also, some of the geostationary weather satellites, like GOSARB, that'll be going up soon. And so what we're going to look at is a satellite that is in geostationary orbit. And there are several that you could choose from, and I'm going to talk about that for a second. But this is the instrument, and it weighs about 150 kilograms, which is very much on par with something that could go on a communication satellite, where you just rent the satellite. Then there's a communication satellite that just leaves you some space on the bottom of it. Takes about 150 watts of power, and the data rate is not that high. And this is something I've been working with Chris on for a long time, because we keep proposing it, it keeps getting rejected for various reasons. But it would be a 4-channel spectrometer. It would measure total oxygen, because that gives you kind of the total amount of air. You want to make a concentration measurement. And CO2 in 2 bands, 161 and 2.06. And that gives you total amount of CO2 in the atmosphere. So now you got total amount of atmosphere, now total amount of CO2, now I can get a concentration. And we do the same thing by adding 2.34. That also gives us methane and CO. Now this is exactly what OCO, the Orbiting Carbon Observatory, or JPL's, was to have been. And in the early days, this was it. But then they de-scoped and took this off. And so they just have oxygen and CO2. This system, though, by staring, gets you actually a signal to noise that's twice as good as OCO's. We actually get to be twice as good by staring, but because we don't measure anything over the ocean, we don't need a polarizer, and for other reasons. And so we actually get another factor of 2 in there. But here's the key, and this is the important part to think about. We're looking down, and there's a slit in front of the telescope. And that slit, when projected onto the ground, is about 3,000 kilometers north-south and about 6 kilometers wide. Now, because you're looking down at a curved object, there is some distortion in that as you go north-south, but you're a long way away. The distortion is not that much. So just for simplicity, think about it as a slit on the ground. It's about 3,000 kilometers north-south and about 6 kilometers wide. And then as the light enters, we chop the light up so that we chunk it up in 3-kilometer batches going north-south. We have a CCD back that's got 1024. That's why we do that. Okay? Then we stare for 4 seconds, and then we move the slit half a slit width. So now we're moving it every 3 kilometers, east-west, and 3,000 kilometers north-south, chopped up. Okay, and when you do that, you can start now thinking about sweeping out areas and map them every 3 kilometers. Every 3 kilometers, north-south. So this is that north-south slit. It's always the same. That's the north-south slit. And then this is how long it takes to sweep across 3 kilometer by 3 kilometer, staring for 4 seconds. So this is, in some sense, this is the mapping time, you will. Now, we don't make any measurements over the ocean. You'll see us looking at the ocean, but that's just, we're trying to include the, we're only able to measure, we're not looking at the glint or anything like that. We just measure over the land, the reflected sunlight. And so here are 3 orbits. You could put it at 70 degrees east out over the Indian Ocean, and this is what you could see at 110 east, more or less right up above Singapore. This is what you could map. Or if we're sitting right out here at about 85 degrees, 90 degrees west, this is what we could map. And this is the one I want to go to. So here's what it looks like. So you could look at the whole tropical forest every 2.3 hours. I mean, you map it every 3 kilometers. You can look at CONUS, the 48 states, about 2.5 hours. So if you add these up, you know, this is a little over 8 hours, about that 10 hours. This is what you could see. You could almost do that twice a day, not quite, but you could almost do that twice a day. You could do this. I mean, these are. You could do different kinds of things. You could, let's just have a measurement campaign. Spend a whole month just looking here, or just look there. Every 3 kilometers. So once again, to look at this, I want to show you what it looks like over Mexico City. So I apologize for a little bit of the noise in this crap, but here, this right here, that's the slit. Now, it goes longer than that, and then it's, you know, but I'm just looking at a piece right here, okay? And just looking at the Mexico City piece, that is that slit. Now, it goes 3,000 kilometers. That's the slit. But now I'm going to move it over half a slit width. This checkerboard pattern that you get, that's the sampling. Now, compare that with OCO. Here's OCO, say on day 1. OCO comes through. 8 days later, the next time OCO comes into this space is here. 8 days later, here. Okay. You could do the same thing. You could look at Boulder to here. I mean, you could look at all. I mean, this is just a chunk of real estate. And this is what geoCARB does every single day, if you're looking at that area. But remember, you could do different combinations. But this is the sample density if you're looking at this area. So we think this is a terribly powerful idea. We made some calculations. Now, I don't want to spend too much time with this, but I just want to give you a flavor for one of the kinds of calculations you do. It's kind of a Bayesian type calculation. What we do is we say, okay, we're going to take, if you will, our best guesses at the carbon cycle right now. And the reason you kind of do this Bayesian analysis, one reason you do it, and there's a lot of debates about this, is let's take what we think we know, and at least use it and pretend we know something. Now you have to be careful with that because we used to think we know that the land played no role whatsoever, and we were wrong. But maybe we're better now. So if we think we know, and we take this and say, okay, let's take 2 land models. Take 2 land models, CASA, and as a land model, and say that's what we think we know. And then let's take something about our uncertainty. Well, just take another land model. So take LBGJ and say, well, this is some measure of uncertainty over the land. This is some measure of what we think we know, and this is some measure of our uncertainty. Do the same thing for the ocean. Take the NCAR, or take Takahashi. This is the measurement-based model or estimating procedure for getting what we think the ocean flux is. And let's compare that with the NCAR model as to give us some uncertainty. And then let's take the CDAC fossil fuels. We should have added we should have put an uncertainty in here, but this was one of the calculations we did. We didn't do that. We said, let's just assume that one. Okay, and then what we do is we say, okay, take this information, then create an atmospheric concentration based upon these fluxes, then sample into TM5, and then sample that at a 1 degree by 1 degree sampling. Actually, no, sample it with the geoCARB mission, wall to wall, and then at the 1 degree level, report out how much uncertainty did I take out of the system by the measurements. In other words, how much did I close this uncertainty? So if you take those two models, CASA and LBJ, and you calculate some kind of uncertainty, and you look at, say, the month of June, you get a lot of uncertainty. And it's really interesting. I mean, you're uncertain in the core belt, you're uncertain. I mean, this is a measure of your uncertainty. And in just 1 month of observation, 1 month of observation in June, not changing, not doing a campaign mode, using that original scan thing that I showed for the Western Hemisphere, where I said, and we're just looking at the CONUS once a day, takes about 2.5 hours, I recall. In 1 month, you get this kind of uncertainty reduction. Now, this is at 1 degree by 1 degree, which is what those models are running at, or half degree by half degree. You're going to get information. You're going to get constraining information that constrains processes. And you're not going to get that with OCO. You're just not going to get it with a sampling mission. It wasn't intended to be. So that was one country. We then said, okay, what if you do this? Let's go into Brazil and kind of take those same modeling framework, but let's tweak one of the models. And let's pretend that we have a 5% increase in primary productivity associated with CO2 fertilization or associated with something. And said, okay, put that in as your uncertainty. It's there and it's not there. Now, then do the same kind of thing with TM5, do the same kind of thing, and now go in and see if you can reduce that uncertainty. Okay, where the uncertainty is coming from CO2 fertilization. And here, what you get with that CO2 fertilization term, basically where you have high productivity, you have more uncertainty, but that's by definition because we stuck it in that way. We amplified the GPP, we amplified the gross primary production due to some assumption, maybe CO2 fertilization, could be something else. We didn't say. And then let's observe the thing and then see what the uncertainty reduction that you could actually say is, and you get tremendous uncertainty reduction in an annual number. Yeah, actually, this was for the month of August. You even get some uncertainty reduction in just a dry month. Now, I will tell you, this particular calculation depends, so is the US, it depends on something that we're not so sure about. And that is, we're having to guesstimate cloud cover. We don't have a good 24-hour, day-by-day cloud cover map for the planet. Sounds crazy. But if you think about it, we got a lot of imagers out there that are in low Earth orbit. And they come over at the same time every day. Take a MODIS data set. Hard to take CloudSat. So you're going to have to come up with some kind of artificial filling in of the other hours in the day and night. We're only looking in the day, but you have to come up with something that makes sense. Maybe we were too optimistic here. I don't know. I talked to Philip Sias, and he talked with UMETSAT, and they're actually interested in producing a cloud map, 24-hour cloud map for the planet. What they do, they take all the geostationaries, they take the LEOs, kind of take some modeling, and produce. I think this would be really, really valuable. Okay, so let me just end with something I want to make sure we're all on the same page on. This is a tough problem. This is a tough problem. And Goethe and Faust and Keeling and Leonardo da Vinci, I think, had something to say to this. And here's the bargain part. I think most people know this, but it certainly was at Paris. And we ain't there yet with Paris. And that is, Suppose you stabilize the emissions of CO2. Stabilize the emissions. Which, if you remember those graphs, when I went to the policy part, growing 2% per year. It's not stabilized, it's going up by 2% per year. Emissions efficiency wasn't offsetting it. So we got to do some work to stabilize the emissions, stabilize the emissions, stabilize the emissions. This is what happens in the atmosphere. Stabilization of the emissions do not stabilize the concentration. Why? 50% stays in the atmosphere. Constant emissions means constant growth of the rate in the atmosphere. So this is what you have to do. You got to get it down. This is what I was saying a few minutes ago. You got to get about 8 billion tons out of the system. You got to cut it by 80%, and then you can stabilize it. But the other thing we have to realize, and this is from the fourth assessment report. I think this is one of the most provocative statements in the whole IPCC. Warming and sea level rise would continue for centuries due to the timescales associated with all the processes, even if greenhouse gas concentrations are stabilized. You know, you like a child, you're throwing pebbles into the pond, and somebody comes by and says, oh, don't throw those pebbles in the pond, you're making ripples. Okay, well, but the ripples continue. It takes a while for the ripples to die out. That's exactly the same thing with warming. Precisely the same thing. Okay, thanks very much. Appreciate it.
Thank you, Gerald. That's fascinating. We have time for a few questions.
Yeah, any at all, anything. Yeah.
Does the carbon observing platform you described, have you envisioned how it would help with mitigation, not just a better uncertainty reduction in what we understand about the—
Well, I think that one of the big questions is what are policies effective? And I had the opportunity to talk with the mayor of Paris when I was over for IPCC, because we actually put in a ground-based observing system in Paris during COP21. We had a laser-based system shouting lasers across Paris and getting CO2 out of the reflected light. And she said, you know, what I'm thinking about is going to an odd even license plate situation where Monday, Wednesday, Friday, even plates can be in Paris and driving, and Tuesday, Thursday, Saturday, odd. Sunday, none. And then you would switch it so that even and odd switched. She said, but you know, would that have an impact? How would I know? If I do something that is highly visible and highly provocative, and someone says, yeah, but how do you know it's going to happen? And we know that you can't get that out of a couple of sensors in Paris. You just can't. We saw that much when we put the green light system in, where we were measuring the footprint of Paris every 5 minutes. Those 1 or 2 sensors that they have for CO2, they missed a lot. And so this would be a real good question here. I mean, one thing we know from one thing we know when we talked about cap and trade, and one thing we know right after Kyoto, when you ask countries what they were doing, every country was a sink for CO2. So CO2 should have been plummeting in the atmosphere because it's easy to fib. And fibbing is easy. And if you think about cap and trade, that's a very fundamental weakness in cap and trade is because you can fib. And so you got to have something that is absolutely there, that is independent, that is measuring this thing, and it's got to be daily. It's got to be looked at all the time. And it can't be different. That's one thing that's tough. If you try to do this with towers, you have different sensors in different places, the inter-tower calibration, very tough problem. So we actually allude to that in the proposal that we've submitted, but we're scared to go too much down that path because somebody's going to say, oh, that's monitoring, it's not science.
Any other questions?
Yeah, any questions at all? Yeah.
How are we trying to connect the science with the policy? Because I know a lot in the political debate, there are a lot of people who don't necessarily believe in climate change. And how do we turn that science into something that they can understand and really get behind so that we can get these numbers down?
That was one of the reasons that I said at the beginning, I'd like to begin with what we know, think we know, what we don't know. Because people like to confuse that. They treat the Keeling Record as some kind of guesstimate. And with the uncertainty of changes in precipitation, which is crazy. I think the second thing is that somehow we have to depoliticize this. And I have an opinion about that, and it's not popular, certainly not popular with my political preferences, which are strongly Democratic. But I think that Al Gore helped politicize the problem, unfortunately. That under Ronald Reagan, of course, he was against a lot of things like acid rain, stuff like that. So he's no great environmentalist, but like he knew the climate change thing was real because Margaret Thatcher said, "Ronnie, trust me, it's real." That's all he had to do. And we got the Global Change Research Program. It was drafted under Reagan, signed into law by Bush the Elder. But we somehow in the 90s politicized it, and then it stayed political. And you sure see that now. I lectured when I first got out to Oklahoma. I was invited up to what they call the Petroleum Club. Very nice lunch. And I taught a lot about safety. And I had just nothing but knowledgeable questions. They knew all of this. And other things that we didn't talk about, like carbon-14 dilution when you burn CO2 and so forth. The reason being is it's, natural gas, if you can get rid of the methane problem, the fugitive methane, that's a good replacement for coal. Certainly, you don't need these coal-fired power plants down in Texas. And turn them all over to natural gas, and you cut some of your emissions down. And then sequester that. I think somehow we have to get back to a rational discussion. I mean, CO2 is greenhouse gas, long lived in the atmosphere.
I think it gets back to your slide that said, how do we transition the economies? That's, to me, the heart of the question.
Huge problem. You actually, I talked about this. I went back and I looked at the largest in everything. The largest nuclear power plant, the largest wind farm, the so-called London Array, the largest solar electric, the largest solar steam, largest windmills, and so forth. And you hit some tough numbers. I mean, right now, wind and solar produce about 2.5% of the electricity for the United States, and that's growth rate of electricity in the United States is about 2.5%. So that means you have to double your wind and solar capacity every year in order to get not more in fossil fuel than debt, if you will. So you got some tough problems. What you got to do is you got to get that GDP emissions factor going down faster than GDP is going up. Because you can't say, well, we'll solve this by stopping the economic growth. I mean, that's what people say. Oh, that's what you're after. So you got to get at that problem.
But carbon capture storage is then.
Carbon capture and storage has got to be part of the equation. And then you say for the mobile systems, either you're plugging in a car into a renewable power plant. I mean, Californians love to plug in their Teslas into some power plant that's in Nevada, burned by coal, and claiming this is a good idea. But if you plug it into a renewable, then it's a good idea. And electricity is sufficient that way. And then maybe use biofuels, not from corn or something you grow, but I mean just waste for jet fuel. But if we don't do these things, this problem not going away. I mean, you can talk about a lot of things that will just go away. This problem not going to go away. I mean, look at the Keeling Record. I mean, look at the Keeling Record. It's a change. We're above 400 ppm now, permanently above. So I think the only way is some form of dialogue. That's where climate science centers can play a really important role. And I think the communications area is just enormous. And I think we should just bungle that time and time again.
Well, thanks again.
Yeah. Thanks, everybody.
Next week, we have Keith Washington, talk about cropping system. No?
Shannon.
Oh, I'm sorry. Shannon McNeely's here. Then Keith is after that.
I got to call the Lord, so I'm afraid of probably just.
Okay. Oh, yeah. Chris.
Thank you.
One question.
Yeah. So this sensors integration that we can attach to existing geostationary satellites or